Our next speaker is Preeti Raghavan. She is a senior NLP research scientist at MIT IBM Watson AI Lab. And she's here to tell us about their work on electronic health records question answering systems. Please welcome Preeti Raghavan.
Hello, everyone. My name is Preeti Raghavan, and I'm a research staff member at the IBM Research Office based out of Cambridge. I'm also part of the MIT IBM AI Lab, and I work in collaboration with Professor Pete Solowitz on this very problem, which is EHR question answering, which is what I'll be taking you through today. So, electronic health records have become more and more prevalently used across hospitals in the US. Um, More than 95% of hospitals have implemented some form of an EHR system, inpatient or ambulatory. Now, an EHR or an electronic health record essentially stores patient records in unstructured and structured formats. Now, in an unstructured format, you have your clinical notes or clinical narratives, which consist of admission notes, history and physical reports. There could be lab reports, discharge summaries, and so on, essentially capturing the symptoms, conditions, and problems that the patient presents with, the tests that are done, the treatments that are administered, the medications that have been prescribed, and how the patient responds to it, and continued care of the patient over time, which is what makes it longitudinal in nature. Now, given that this is medicine and these are physicians or medical experts noting a patient's history, you have a lot of domain specific medical terminology used in these notes. And then there is your structured data, where typically a patient's lab records, medications, discharge conditions, perhaps encounters, chart events are captured. Now, both of these sources are important in capturing the patient's information. Often, at least anecdotally, physicians prefer clinical notes as they can freely enter the information they want about a patient. Whereas in structured data, it's structured, so you can capture values or measurements more easily, like lab readings or vital measurements, or medications that are started or stopped over time, or conditions presented on admission. Now, these uh, forms of information in a patient's EHR are a gold mine of information that are typically manually browsed through by a physician, perhaps using some sort of an EHR system. Now, take this example of a bunch of notes generated for a patient over time, starting from an admission note, a pathology report, a radiology report, a bunch of progress notes, perhaps as he or she is, in a hospital for a chronic condition, and a discharge summary. Now, the information captured in these notes range from different conditions, tests done, scans done, references to past conditions. So there are references to the same medical event across notes. So those are co-references. There could be everyday progress that refers to past medications, future plans, and a discharge summary that sort of summarizes the patient's stay, say in a hospital, starting with why they presented, how they were treated, assessments, and then plans for the future. Now, all of this information together, if analyzed, could be, if automatically analyzed, could be very, very useful to clinical care, which is where NLP comes in, natural language processing, where there have been, in the last decade, there have been several efforts to try and extract useful information from these clinical records, especially clinical notes. There were the I2B2 or N2C2 challenges, which were done for a variety of tasks, including named entity recognition, relational learning, temporal relations, co-reference resolution, and so on. What this allows us to do is extract important entities, relations from these clinical notes and reason about them. Allow the computer to reason about them to give us, in an automated fashion, certain useful things. Perhaps these underlying NLP tools could be used for applications like automation of clinical trial recruitment, helping with clinical decision making, um, like predicting readmission for a particular problem, or going through tons of patient records to sort of at least semi automate the patients who satisfy a particular eligibility criteria for a clinical trial. Given in light of the current COVID pandemic, it's all the more important. Such problems become very important. Um, and then, of course, given the development of state of the art neural methods, there have been pre trained models on large scale medical and clinical data sets, including BioBird, ClinicalBird, PubMedBird, and so on, which allow us to develop and apply state of the art neural methods on clinical data. And finally, there's question answering, which is another way of looking at the information that is across the structured and unstructured data in the node. And what that allows us to do is answer a question, whether simple or complicated, in a precise manner. And in our work, what we focus on is questions asked by physicians on clinical notes, on a patient record, on a single patient's record, as opposed to a cohort of patients. So here is an example. Here you can see a snippet from a clinical note. And the question that's been asked is, has the patient ever had an abnormal BMI? The evidence for that is the text highlighted in red. Similarly, there's another question: when did the patient last receive a homograft replacement? And you can see highlighted in blue the answer. So these are questions asked off of clinical notes in a patient's record, and the answer is a span of text in that clinical note. It could be multiple spans of text within a clinical note or across clinical notes, and this is the problem that we try to address. So automatic question answering has made several big strides in the general domain. There have been several reading machine comprehension systems, including Squad, that have been built in the general domain. There are several leaderboards and several large-scale annotated datasets. However, applying these models and datasets in the medical domain has several roadblocks, and that is because the medical domain, of course, comes with certain differences. Here are a few, which is the clinical discourse in, say, your clinical notes is temporal in nature. There are many temporal expressions used. There are references to medical events in the past, and in light of what is happening now to the patient, these things need to be reasoned with. And of course, it's longitudinal. There are notes generated over time. There are several admissions over time, making the discourse different from a single document that is the only document that you're considering in answering a question. Often, QA systems rely on a fact being redundant across several sources, which is very useful in fact-based question answering. However, in clinical data, patient-specific data, there's little to no redundancy of facts. Something that happened to a patient may be mentioned a few times across notes or may not. Of course, there's domain-specific terminology. There are often misspellings, incomplete sentences, random lists that go in between data. There's several copy-paste, things that are popularly known in studying clinical records, which are very, very difficult because you cannot use NLP tools, for instance, that have been trained on general domain data on clinical text easily, because they would break. They've not seen incomplete sentences. They've not seen domain-specific words or misspellings. And then finally, the biggest problem, I would say, is privacy concerns about PHI, personal health information, making it very difficult to collect large-scale annotations for training. And this is essentially a very big roadblock because one, you need medical expertise to annotate, and two, that along with privacy concerns makes it very difficult to crowdsource annotations. So you essentially need a bunch of physicians or medical experts sitting and annotating data for you even if not for training, at least for evaluation, offering credibility to the data set. So the gist of this is that while it's possible to transfer many of the techniques, they have to be adapted with these domain specific differences in mind to work well on clinical data. But the first roadblock is a lack of a large scale data set for clinical question answering. And these are for the reasons I just stated. Generating a large scale data set requires time, it's tedious, requires a medical expert, several medical experts, and this takes time, it's tedious, and you probably cannot generate something large scale unless several years go into it. So, in order to bridge this gap for question answering, what we did was to repurpose existing annotations that exist for other NLP tasks in the clinical domain, like, say, the I2B2 tasks that were put out for medications, relations, co-reference, and so on. Now we have these annotations. What we did is to repurpose those to create a large-scale question answering corpus with over 1 million questions, logical forms, and answers that would help in question answering. Now, briefly, how we went about this was to first collect questions from physicians. So we polled physicians at the Mayo Clinic, at the VA, at Cleveland Clinic, to gather an initial pool of questions. Now, these are real world questions that those physicians would want to ask off of medical records. However, we have no answers to those. So what we then did was to create question templates, which is we normalized the medical entities in those questions and created a template. So what is the dosage of nitroglycerin would become what is the dosage of medication, because we normalized it and inserted an entity placeholder there. Now, an expert or a medical expert would annotate a logical form for this question. Here you see medication event, medication dosage equals X is the logical form for this question, and here you see a slot-filled logical form. Now, given this question and given the logical form, what we do is we slot fill these question and logical form templates with annotations from these several I2B2 data sets for different NLP challenges. We do that by mapping entities across the two with the help of an ontology or schema representation of the data. So what we do is come up with a schema for the domain, for the EHR domain, where you have a patient who has entities such as conditions, medications, treatments, and these are related because you could give a medication to treat a problem and so on. So we have the schema from which these logical forms are instantiated, and then we have all of these annotations in this data which are used to slot fill these logical forms and questions and also generate the answer. As you can see here, nitroglycerin dosage equals 40 milligrams. Nitroglycerin goes into the slot filling of the question and logical form, and the 40 milligrams goes into answering the question. This is a simple example from the data set. There could be far more complex examples when, say, a relation data set is considered. But what this allows us to do is eliminate the dependence on a medical expert in annotating spans of text for a question and saying that this is the answer. This becomes especially tedious when you go across notes, as we do in the heart risk challenge, which is longitudinal in the I2B2 datasets. So what this allows us to do is use a semi-automated process to generate a large-scale dataset. It's semi-automated because of the logical form annotation provided by the medical expert. However, this very annotation lends credibility to the dataset, because what this logical form does is it is a structured representation capturing answering needs expressed in the question. So dosage of medication becomes medication event dosage equals X, and this allows us to easily and credibly slot fill the question, logical form, and also generate the answer. Now, given this data set, we tried a state-of-the-art QA model back then, which was DRQA. And when trained on emrQA out of the box, we got a mediocre F1 score of about 60%, which says that there is room for improvement in light of all of the domain-specific differences that I pointed out earlier. So briefly, the emrQA dataset gave us over 1 million question answer and question logical form pairs. This is community shared, so it allows for researchers to use, critique, improve, as well as benchmark their models on this dataset. The use of logical forms as an intermediate not only lends credibility to the dataset, it also allows training models where if we use the logical form, which is a structured representation capturing the answering needs, we could sort of justify the answer. And as long as it is satisfying the logical form, we can say that the question has been accurately answered. And again, given logical forms and their traditional use is in semantic parsing of questions. So given a natural language question, we could parse it to the logical form and then map it to any query language, which is especially useful in answering from the structured portion of the EHR. But perhaps there can be applications of it even in training models for answering from the unstructured portion, which I will get to. And while emrQA, of course, has its limitations, it is noisy. We do over-generate on each of those data sets, which is why it is so large scale. There is definitely a subset of emrQA that consists of questions that are challenging, that involve resolving relations. It requires inference across sentences, and it also requires domain knowledge in answering those questions. Now I'll briefly talk about how we use emrQA for benchmarking two problems. One is that of semantic parsing and the other is that of question answering. Briefly before that, another characteristic of emrQA is that it has several paraphrases. And a paraphrase, when I say paraphrase, I mean a question paraphrase. And a paraphrase is different ways of asking the same question. So a physician might phrase his or her information need in different ways, but it might mean the same thing, or different physicians might phrase the same information need in different ways. The way paraphrases are defined in emrQA is that these are questions that map to the same logical form. And on an average, we have about 7 paraphrases per question. Now, paraphrases are often, you can categorize them as maybe syntactic paraphrases and substitution paraphrases. Now, syntactic paraphrases are where you simply perhaps rearrange words or introduce some other non-semantic words that don't alter the meaning of the question, and the questions mean the same, like in the first example. Substitution paraphrases are where there is phrase or word substitution across the two questions, but they end up meaning the same. So in this case, is there any mention of problem in the patient's record is the same as has the patient ever been considered for problem. So we see both types, syntactic as well as substitution paraphrases in emrQA. Now, why these paraphrases are important is that given the large number of paraphrases per question, there are about, at the higher end, certain questions have over 40 paraphrases and some questions have just one paraphrase. Why these are important is that it allows us to actually create more realistic splits and also allows us to explore the problem of model generalization. So what happens often in NLP datasets in general is that the same form of the input can also be seen across test data. For instance, take the dataset overnight, which is a semantic parsing dataset. They have a domain called as the recipe domain. And if you look at the questions there, And there could be something like how many X are there, where X would be a certain entity. Now, if train has how many ingredients are there, your test could have how many meals are there. So just the entity replaced form could occur across train and test, making it rather easy for the model to learn that form and or memorize that form and perform well at test time. However, a more realistic way, perhaps, to split a data set would be to put all questions that have the same form in test and make only questions that are differing in form um, in the test set. So the train would have a different form and the test would have a different form. So a form that is seen during training never appears at test time. So, for example, all instances of has the patient ever been exposed to problem would go in train, and all instances of does this patient have a history of problem would never appear in the train set, yet do so at test time. So, this allows us to see if the model can generalize from this to the second form, which is a paraphrase of the initial form. So, is the model able to learn to paraphrase along with answer the question? Because in a real world scenario, a physician may not exactly phrase his information need exactly the way in which the model has seen the question. So, they could phrase it in any way, and the system should still be able to handle it. So, this is a fundamental challenge in machine learning, which is an inability to handle unseen paraphrased observations at test time. And what we do is we address this problem for sequence learning architectures by jointly learning paraphrases along with the main task. Now, we do this for question to logical form learning, right? And logical forms, if I were to remind you, are like this semantic form in a structured form that is capturing the information needs in the question. And each logical form, as seen in the right, may be mapped to multiple paraphrased questions. So, medical event, the same example that we saw earlier, the medical event medication dosage equals X, could map to all of these expressions of the question. How much medication does the patient take per day? What is the current dose of the medication? What the current dose of the patient's medication? And so on. And a robust model should be able to answer variations of this question template without observing it during train time. So it could have just seen one of these forms, it should be able to generalize to all of these forms. In this case, in the problem of question to logical form learning, which is given one of these questions, we want to predict this logical form. So that is the framework that we propose, which is we use an attention-based seek-to-seek architecture, as seen as in this example. Your trained data may have seen these three these three questions, whereas the test data would never see these forms. It would only see a different form or a paraphrase of these questions, and the expected output is a logical form that looks like this. And that is what we want to see for not only the emrQA dataset. We show that the method that we propose works well not only for other semantic parsing datasets like overnight. We also tried it for a machine translation problem from Czech to English, and the data and this method performs reasonably well. So, given a seek-to-seek architecture, in this case, the baseline happens to be a seek-to-seek architecture with copy, what we do is we propose models where we learn the paraphrase along with learning to predict the logical form of the question. So, your multitask paraphrase generation model, what we have is an auxiliary decoder. So during train time, we would also sample a paraphrase of the input question and try to learn. We modify the objective function where we try to learn both the logical form and the sampled paraphrase of the input question jointly. Another model is the paraphrase detection model, where what we do is we again sample a paraphrase of the input question during train time, we encode it, and we modify the loss function to try and reduce the cosine similarity between the input question and its paraphrase. So that is your paraphrase detection model. And then we have a combination of the both, which is of the two, which is paraphrase detection and generation, where your loss function essentially does both. It tries to train an auxiliary decoder as well as reduce the cosine similarity between your input question and paraphrase embeddings. Now, given these approaches, where we try to essentially learn the paraphrase of the question along with the logical form in order to help model generalization, what we observe is, given a baseline of seek to seek with copy, we perform experiments on a random split of the data, which is just randomly split the data into train and test, and on a paraphrase split of the data, where, as I described earlier, only unseen forms or paraphrases of the questions in train would be in test. The same form would never occur across train and test. You can see that the baseline does rather poorly on the paraphrase split. However, with the paraphrase as an auxiliary task or trying to reduce the embedding similarity, we do see a vast improvement in the accuracy on the paraphrase level split. Not only that, like I said, even on other data sets, in this case overnight, we do see improvements on several of these domains when we used our proposed methods. So that was the problem of learning to map from questions to logical forms. And what I described was a seek-to-seek model that has been adapted to domain-specific needs, which is making it more realistic and practically usable as it adapts to different variants of the question at test time. Now, on similar lines, we also explore the problem of question answering. Now, question answering is that given a natural language question, you want a span in the clinical note to be presented as the answer, or multiple spans to be presented as the answer. Now, here we want state-of-the-art neural models that have been presented for general domain datasets to perform well on our emrQA data, and also generalize better, similar to the previous task, on previously paraphrased, previously unseen questions, that is paraphrased questions at test time. In order to do this, one of the things that we do is we predict the logical form of the question as an auxiliary task along with the main task of learning to answer the question. Along with this, we also introduce medical entity information in these models via the ERNIE architecture. And essentially, this allows us to introduce domain-specific information into the models about these entities. And these multitasked entity-enriched models, we observe, they perform overall about 5% better than the baseline BERT model that we try with emrQA. So clinical BERT is a model that was presented that essentially fine-tunes BERT on clinical data. And so it makes BERT more aligned with the way information is expressed in your clinical notes found in Mimic. So there's clinical BERT, and then there's ERNIE, which incorporates entity information into BERT to create these entity-enriched contextualized embeddings of a token. So a motivation of using ERNIE is to use external knowledge that is available in clinical ontologies like the UMLS, and use that to help, at least indirectly help, the question answering process. So what we do is we essentially take clinical BERT, we introduce domain knowledge via the UMLS using the ERNIE architecture, and sort of create this clinical ERNIE for question answering. And this essentially helps the model's ability to generalize better over paraphrases during testing. And for this, since we also introduce the logical form as an auxiliary task, learning the logical form as an auxiliary task, it helps this model's generalization ability. So given a question like how was the patient's extensive liver metastasis diagnosed, and the answer that is marked in this context in green, what we learn to predict is both the logical form as well as the answer to that question. Now, learning this logical form not only helps the model learn better, pushes the model, especially given paraphrases that map to the same logical form, it pushes all of them towards the same answer. It also provides sort of a rationale or justification for why this is an accurate answer for this question, because here the logical form is capturing events and attributes that have been annotated by a physician who says these need to be satisfied in order for this question to be considered as answered. So it helps the model as well as provides sort of a rationale or justification for the answer. So in this problem, what we do is we have our input, which is the question and the context, which gets passed to a multi-head attention layer. We also run the input through MetaMap to annotate it with UMLS entities, and that is again passed through another entity multi-head attention layer. You can see here you have as tokens the semantic types of those entities, and here you have the actual tokens as entities going into this layer. And this gets combined in this information fusion layer, which finally goes to a span selection layer where the answer span is predicted. Now, this information fusion layer also uses a pooled sequence representation, which gets fed to your logical form inference layer that also predicts the logical form. So along with the answer, you also predict the logical form. Now, we ran several experiments, both at a passage level, where the context is a passage, as well as at a sentence level, where the context is a sentence. We also tried this on both random splits as well as paraphrase-level splits of the data. And we observe that in each case, we see superior performance, where we can see in our paraphrase-level split, our multitask clinicalERNIE gives us an F1 score of about close to 79.8%, which is a big jump over the baseline, which is BERT. Similarly, even here we see that we get about 3 to 4% in the paragraph level, passage level context. We get a significant jump over the baseline using our proposed models. So in conclusion, clinical data is challenging to work with because of several reasons, but one of the important reasons is the lack of large-scale resources that can be used for training reliable models that will work well in a practical setting. Now, in order to take steps towards this, what is required is to explore alternate semi-automated perhaps methods to generate large-scale data sets in a credible manner. And we do this by generating the emrQA dataset using a process that utilizes existing annotations and uses the expert input in the form of logical forms and generate a large-scale dataset. While there's a lot of room for improvement in emrQA, it is an important step in allowing the research community to benchmark their models for both semantic parsing as well as question answering. In case of semantic parsing, we propose a new sequence learning framework where we train the main task of going from question to logical form along with a paraphrase learning objective that not only allows us to better learn the logical form, it enhances model generalization and allows us to go to unseen questions that were previously not seen at train time, paraphrased questions. And then for question answering, what we do is propose a multitask learning model where we learn logical forms along with the main task of answering. And we also propose a clinicalERNIE model that allows us to learn token representations for entities. An advantage of entity level representations is that while your clinical BERT is going to align your um, data to look at medical terms, medical vocabularies, what it may not do is learn that two expressions actually map to the same entity, like heart attack and myocardial infarction might map to the same entity in, say, the UMLS. Now, using an architecture like ERNIE and developing a clinicalERNIE allows the model to see such similarities, that different expressions of the same medical event actually map to the same entity, and that helps in better performance of the model overall. Also, again, in conclusion, we are a long way to having a practically usable question answering or a sophisticated NLP system, because of all of the reasons I described. Because we rely on expert annotations, there's lack of resources in generating a diverse and large scale set of questions, but these are essential steps, or the foundational steps in starting this process and getting there. And some other steps that could be taken would be perhaps benchmarking clinical NLP tasks, including QA, using a generic leaderboard task like Glue, where the community comes together and benchmarks these tasks, including QA, summarization, named entity recognition, and so on. And with that, I'll end my talk. Thank you.